right? So the assumptions, the important ingredient here is the case of before and after. Anytime you see the terms before and after in a word problem, we're dealing with a match pairs distribution, right? Or a match pairs hypothesis test, which is a T distribution, right? The null and alternative hypotheses are structured the same way as the two population proportion hypothesis test, except we're talking about means again, because we see a mu in our null and alternative hypotheses, we must be talking about a t-test. All right, so you can see here that the complete graphing calculator approach is right on back to the t-test, but you also see that we have a set of raw data here. Right, so the example talks about 0.05 significance. That's easy enough, at least that part. To test the claim, there's no significant difference, right? No significant difference between anything. No significant difference means that we're talking about equal. This is equal means, right? That's trying to say mu1 is equal to mu2, right? If this is set 1 and this is set 2. Right, so we're saying that this distribution of information comes from a population that's different from this set of information. Right, so set 1, set 2, this one is going to have a population mean. This one's also going to have a population mean. How they relate to one another is going to give us our null and alternative hypothesis. Right. No significant difference. That's kind of tricky because this is one instance where they're actually giving us the null hypothesis as part of the framework of the question rather than the alternative hypothesis. So the only thing that we can do is say, well, the alternative to this would be something other than mu1 and mu2 being equal to one another. And I don't know what that would be. It could be that mu1 is more than mu2. It could be mu1 is less than mu2, but they didn't give me any indication either way. So what I would have to say instead is that mu1 is simply not equal to mu2. And when I say that, that leads us to what's known as a two-tailed test. All right, so this is two-tailed. And the idea is that not equal is the same as greater than or, well, I'll write the word or because the notation can be a little ugly, or less than. So it gives us two possible outcomes. Those are the two possible tails that you can have, all right? So when we draw our graph here, we would want to have 0.05 split up among the two tails or between the two tails. So that 0.05 gets cut in half and gives us 0.025 on either side. So we're going to get two critical values, but fortunately, because the graph is symmetrical, if we figure out one, we'll know the other. All right. So that brings us to Desmos, because they didn't give us any summary statistics. What they gave us was a set of before and after values. So let me open a fresh new calculator. I'm going to pop in a table here. I'm going to title this actually, I was going to title it before, but I forgot it. It only lets you use one character. You can use as many subscripts as you want, but it won't do anything more than one character. So B and A before and after. I'm going to type in these values: 0.4, 0.625, 0.429, 0.65, 0.714, 0.364, 0.5, 0.667, 0.8, and then I get my second column of information here: 0.364, 0.643, 0.667, 0.25, 0.778, 0.6, 0.7, 0.154, and finally 0.182. All right. So when we're dealing with match pairs distributions or match pairs t-test, the only thing that we need to do is actually, instead of finding the mean and standard deviation for each set of data separately, what we're going to do, and I'll just jot it down here and I'll say these are our statistics. We're going to find the sample mean of the difference between the two sets of data. So D for difference. Sample mean for the difference, sample standard deviation for the difference, and then the number of pairs of data. All right. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9 pairs of data. So N is going to be 9. All right. So what I'm going to do is, instead of making a new column of just the differences, I'm going to go to function, under stats, mean, and I'm going to type in B minus A. And it's going to give me the mean. All right. So you're going to type in mean of B minus A. So this is in Desmos B A. And then we're going to do the same thing with standard deviation, also B minus A. And then you're going to round the numbers appropriately, 3 significant digits, so in this case 0.0873. So standard deviation, not the population one, but the typical sample standard deviation, B minus A. Right, B for before, A for after, but whatever it is that you title your columns, that's what you're putting in the parentheses. In this case, 0.331. Right, so it's still a t-test. So our test statistic is actually going to have the same structure as the regular t-test. T is going to be equal to, instead of x bar, it's going to be x bar sub b minus mu sub b over s sub d over the square root of n. All right, so it's the same formula except the subscripts are d's, but as long as you know that this number is going here, get a fresh new one. This number is going here. And this number is going here, you're good. Right? The only thing that might be concerning is that mu sub d. That's the mean difference, the difference between the population means for the assumption. The assumption is that mu1 is equal to mu2. So this should also be 0, just like it is for the population, the two population proportion test. All right, so still a t-test, just a little bit more background work to get things going in the right direction. All right, so there's a lot of things that are incomplete here, but that's because we haven't broken out the t-test calculator. So we do that and we just go right on down the line. It's a 0.05 significance level. That's the default. We have 9 as the end value, so I scroll to 9. Degrees of freedom is 8. That's great. That's wonderful news. Critical values, because it's a two-tailed test. Ignore left-tailed, ignore right-tailed, go to two-tailed. There's 2 values here. You see that they're symmetrical. One's negative, one's positive. So I'm going to put in negative 2.306. And then also a positive 2.306. Once I have those, I shut that folder up. Critical regions, again, go down to two-tailed. We need both of these. See both graphs below. Tap them both on. We'll shade them for you. Then shut this one. I mean, it's weird to say it, shut this one up, but that's what it is. I want to shut it and I want it to go up. All right, statistics, sample mean, 0.0. This one, I'm not going to be able to scroll to it. So I'm going to type in 0.0873. For sample standard deviation, 0.331. The parameters, I'm going to make that a 0. Going the wrong way for whatever reason. So once I have those in and I'm comfortable with them, I can, see it. I moved it, and that's why I close up the folders, because it's very easy to slip and accidentally type over it. All right. So my test statistic should be, well, in this case, it's approximately 0.791. If you compare that with the number line, the glorified number line here, remember negative infinities this way, positive infinities that way, zeros in the middle. I don't know where 0.791 is. I just know that it's not going to be in the rejection area. It's going to be 52, so somewhere around here. That's where my test statistic is going to be. My p-value, again, I want the two-tailed, the nasty looking formula, but all I care about is that 0.45. It would round to 0.452. That p-value, in order to reject the null, that p-value has to be less than the alpha value. If p-value is less than alpha, then reject the null. 0.452 is not less than alpha, so do not reject the null hypothesis. All right, so the null is the keeper. The alternative is the one that's getting tossed. So if we're talking about rejecting the null, whether there's sufficient or insufficient evidence, I'm keeping the null, which means that there was insufficient evidence to get rid of it. All right. Now that null hypothesis is mu1 equals mu2. That's talking about equality between the means, which translates to no significant difference between those two population means. So there is insufficient evidence to reject the claim that there is no significant difference. I'm just rephrasing it. Between average winning percentage. Now I got to shrink it down. I know it's a pain to write this much, but in order to get the idea across, you got to get it all in there. Average winning percentage before and after a bye week. Whatever that is. All right, so there's insufficient evidence to reject the claim that there is no significant difference. That means mu1 is equal to mu2 between average winning percentage before and after a bye week at the 0.05 significance level. The alternative hypothesis is irrelevant. We only needed that to conduct a hypothesis test. They weren't asking about that. They were asking about the null. So once I wrote the first sentence, I was done with my conclusion. All right. The only reason we ever have to write more than one sentence is because most of the time the questions that you're being asked involve the alternative hypothesis. So this is irrelevant, so you can disregard it. All right, but I always put it in there anyway, just in case you need it, as part of the template.